Welcome to DCL 303. This will be a continuation and I guess a conclusion in a discussion of basically how sideband and AM are generated and transmitted. Now I'm going to again talk about the vintage analog version of how to generate sideband. It's not really my intent for you to understand the intricacies of old equipment. It's more my intent to help you understand what sideband is, what AM is, and how the signals work and how they can mix. So I really want you to understand what the signal is more than how the equipment works. The last time we generated an upper sideband signal. This time I want to show you how to generate upper or lower sideband, either using filters or other techniques. There are actually a couple of ways of selecting a sideband. I'm going to show you the two major ways of doing it that were used in analog days. We'll also talk about, since the filter obviously operates at only one frequency, how do you generate all the frequencies we really want to talk on? We'll get into that too. The easiest method to understand is to simply select the sideband you want with filters. Of course, it takes more than one filter. Here's our original design. And we have the good old 3 megahertz or 3000 kilohertz carrier. Speaking into the mic, we generate both sidebands at the same time. We filter for the upper. It passes. We reject the lower. And this is the filter we use. However, if we were to design a new filter and take a close look, the carrier frequency is still 3000 kilohertz. It's just the response of the filter has been shifted down by 3 kilohertz. We pop the new filter in, and generating the same sidebands with the same carrier oscillator frequency, we now pass the lower sideband, reject the upper sideband, and only the lower sideband makes it out. As you can see, switching a filter in is really a very simple way of doing this. It works every time it's tried. It's very reliable, but it was almost never used. And the reason you would never do this, or almost never do it, is the most expensive item in the radio was the crystal filter. So if you were really concerned about cost and profit, which of course everybody is, you would probably try to find a way to do all of this with one filter. And you can do that. In fact, the majority of ham equipment was done with one filter, although there were some military and commercial products, and I believe some early Collins equipment that actually had 2 filters in it. But for the most part, you didn't see this. So let's look at how it was done. So with offset carrier, the first thing we do is we shift the carrier up. Notice now the frequency is 3003 kilohertz or 3.003 megahertz. We're using the same filter, but now look what we're doing. Before, we generated these sidebands. When we change the carrier frequency, the sidebands all change by the same amount. They go up by amount of 3 kilohertz. This means that now our lower sideband fits the filter and is passed through, and we reject the upper sideband. Now, how would we do this? Well, we'd put a little switch in here and just tell the carrier oscillator which frequency to run, and we would label the switch with the sideband that the filter will pass at that frequency. Here, I flip the switch to the other position, so now I get the upper sideband. In fact, I'm building well, I guess I can't call it an antique transmitter because I'm building it, but it's antique technology. There's a tube on the other side of this tube socket. This is my crystal oscillator or my carrier oscillator. Here's my lower sideband crystal, my upper sideband crystal, and the switch that I use to select between the two. This is the CW crystal. I'll talk about that in a later video. What we have done is we've used the technique called offset carrier. But we've created a problem because when you think about it, when I go to lower sideband, I'm generating the lower sideband for a different carrier frequency. So when I flip the switch from upper to lower sideband, my frequency display must jump up 3 kilohertz. So that means every time I select a sideband, I've got to readjust my dial. This is not a big deal, but it's a little annoying. I'll show you in a few minutes how we fix this problem very easily. Let's talk about heterodyning sidebands. Now, a heterodyne is a signal frequency that we create by combining or mixing two other frequencies. So we call this heterodyning. We could just say we're using a mixer and we're mixing to a new frequency. But heterodyne is the technical term or the dictionary defined term for what we're doing. Here we are with our original upper sideband signal coming through the crystal filter because we've got an exactly 3 megahertz carrier oscillator running. We must mix the signal up or down to a frequency we can use on the air, and heterodyning can do that for us. We really want to have a way of varying our frequency of operation. Heterodyning can do that for us. And we want to fix the carrier offset problem so the frequency display doesn't jump every time we change a sideband. And again, heterodyning can fix that. Here is our upper sideband configuration. Notice I've added a VFO, which is a variable frequency oscillator. It will run from 5 to 5.5 megahertz. This gives us these two products here. If this is a balanced mixer, we only get the sum and difference. We don't get the original signals. So if we use a balanced mixer, we get a rather clean output. As you can see, we mix the signals and pass them through a filter, and now we have shifted ourselves up 8 megahertz. If we shift the VFO up another half a megahertz, notice the output goes up a half. So now we've provided our way of a variable frequency. So that problem has already been resolved, just with the VFO. We're still not on an amateur or commercial frequency we want, but at least we can vary our frequency. Now, let's see if we can fix the carrier offset problem. Remember when we shifted up to 3.003 megahertz, or 3003 kilohertz, we generated a sideband 3 kilohertz too high. So how can we fix this? Let's take a look at our transmitter design. And remember, we're 3 kilohertz too high, which means these frequencies here are 3 kilohertz too high. At least when we're in the lower sideband switch position. So we have this switch here, right? How about if we tried this? Let's connect a wire from here and run it over to here. We'll set the equipment up so that when the switch is in the lower sideband position, the VFO drops exactly 3 kilohertz. Now, look at what we have. We have a signal 5 megahertz higher than the frequency we should have generated in the first place. We have just fixed our carrier offset problem. And this was a very common way of dealing with the carrier offset problem in the days of balanced modulators and crystal filters. How far have we made it so far? Well, we found out that heterodyning fixes a lot of problems. We only have one problem left. We are not on an amateur or commercial frequency. We're in this weird area between 8 and 8.5 megahertz. Now that we fixed the offset problem, let's go back to the first design, 3 megahertz oscillator, upper sideband, and with this being a balanced mixer, we've just got these two mixes here, the sum and the difference. We're going to filter for the sum. So let's look at this. We'll eliminate everything before the crystal filter. We'll just ignore it for now. How about we put an oscillator in with another balanced mixer? And we can set the oscillator up to put out a frequency that will give us our ham bands. If we filter for the difference, we can inject these frequencies and get 80 and 40 meters. If we filter for the sum, we can use these frequencies and get the upper bands. Well, let's see. First of all, there's a couple of problems. The first problem is the sum and difference on 40 meters are so close together, you're never going to filter them all that well. The other problem is it's kind of clumsy to use the sum for some bands and the difference for other bands. You can do it, but it introduces a few confusing points. So in general, this is a bad idea. Fortunately, this is a workable idea. We've raised the oscillator frequency so high that we can always take the difference. That does a lot for us. First of all, notice the difference between the sum and the difference is tremendous in every case. That means the tuned circuits past this mixer are going to have a very easy time filtering out the frequencies we want and rejecting the ones we don't want. So we're doing pretty good. But let's take a look at a little math. If we were to say go for 80 meters, what we are really doing is we are mixing the 12 megahertz signal with the 8 megahertz signal, and we're interested in the difference frequencies. But the difference frequencies look a little weird. Take a look at this one and this one. What do they look like? Well, don't they look very much, if this one looks like this one looks like this one. We've created a problem by taking the difference frequency, and this is one of the things I really wanted you to see. By taking the difference frequency, if you sit down with a calculator, or if you stare at this slide long enough, you find out that by taking the difference frequency, we commit an act of sideband inversion. We generated an upper sideband, but now we're going to transmit a lower sideband. And it works the other way. If we had generated lower, we'd now be transmitting upper. Of course, there's an easy way to fix this. And the way is, since it's always backwards, the one thing that we can do is to go up here and change the label on this switch. Relabel the upper one upper sideband, the lower one lower sideband. Because the inversion happens on every band, all we've got to do is relabel the switch. Once we do that, all of our problems are behind us. And that's it for single sideband. I took you through all of this, again, not to teach you how old equipment works, although I hope you did find it interesting, but just to give you an idea of some of the fun mathematical things that go on. The sideband inversion trick is something I encourage you to sit down with a calculator and prove it to yourself, since I probably went through it rather fast. It's not a handicap. In fact, there are times when inverting sidebands does exactly what you want to do. Just keep in mind that in conventional AM, the content of the upper and lower sideband are identical, so it doesn't really matter which sideband we filter for, insofar as the information being transmitted is concerned. What matters is that we're on the right sideband for the band we're on or for the person trying to listen to us. I hope this has been helpful and informative. I also hope that it's been fun. If you really want to read about generating sideband and balanced modulators, the third reference on the screen, if you can find it, and I believe you can find it online, is the best reference I've found anywhere. Thanks for watching. The next video in the series will be on FM, and the one after that will be on the digital voice modes like DMR and Fusion or D-Star or C4FM. Thanks for watching, and I'll see you next time.